Hello and welcome back, everybody. We've talked about recently the fact that work and kinetic energy, or any kind of energy, are the same thing. And we took a kinematics equation and plugged our values for work into it, that is force times distance, and got a new value, which is kinetic energy, that is 1/2 mv squared. And or our final kinetic energy is 1/2 mv squared, and initial kinetic energy is 1/2 mv initial squared. And so if we have a change in kinetic energy, final minus initial, and I should have some final subscripts right here, v final right there, 1/2 mv final squared minus 1/2 mv initial squared right there. Well, that means a change in kinetic energy. Delta K. Sometimes I write it with K, sometimes I write it with KE. But what we figured out in the last section was that the net work that was being done, net work, the most basic definition of net work is being force, or net force, times distance, is equal to a change in kinetic energy, final minus initial right here. Think of it kind of like this. If you have a ball on a track, all right, and there's a box sitting right here. Here's your ball, and it rolls down the track. It has kinetic energy. Okay, it's got energy, but it hits that box, all right, and it pushes that box some distance. So going from here to here, that's some distance. Well, that's work being done. It takes a force to move that box that distance, and that's work being done, which means your kinetic energy right there and your kinetic final energy right there are going to be different. You're going to have less kinetic energy in the ball because some of that energy went into moving the box, the work required to moving that box. And that's what we call the work kinetic energy theorem right here. That any work that is done results in a change in kinetic energy, usually a loss of kinetic energy. And we call this the work kinetic energy theorem. So as work is done, kinetic energy changes. Let's see if we can apply that to an example right here. Okay? Example 8.5, we've got a box of books being lifted up. Right off the bat, I'm going to draw a diagram right here to sort of illustrate this, and then probably what I'll do is I'll shrink it all down so that we can have a little more space to write. I can do a better box than that. Let's see. Somewhat rectangular right there. Okay. And I'm going to do a dotted line. I oftentimes do a dotted line to indicate a distance that an object has been moved through. And there's our final box right here. So down here we're going to pretend that's just the ground right there. Okay. So we've got a 4.10 kilogram box of books. All right, well, that's our mass, right? The mass equals 4.10 kilograms. You can go ahead and write that down as one of your givens. Is lifted vertically from rest. What does that tell us? From rest. That means the initial velocity equals 0 meters per second, right? A distance of 1.60 meters. Okay. Now, in the past, we've called distance or displacement delta x, but in this chapter, we're just going to call distance d. All right, because it could be delta x, delta y, it could be any distance right here. We're just going to call it d, and so our distance is going to be 1.60 meters with a constant upward applied force of 52.7 newtons. All right, so that's F. A for applied. So our force applied is 52.7 newtons. Okay, that's a point in there next to the 2. Find the work done by 3 things, really. The person lifting it. So the work by the applied force, that's A right there, what we want to find. B, we want to find the work done by gravity. And we want to find the final speed of the box. So that's V final of the box right there. Okay? So let's go ahead and see if we can find the work done by the applied force, that is the person applying force to it. Actually, you know what? Before we do, real quick, I should probably label these on the on the diagram. Okay, the applied force F A, that's upwards, right? That's 52.7 newtons. Okay, but there's not just an applied force upwards. There's also a downward force of weight caused by gravity. So mg right there. Some people call it just W, but of course we call it mg. That directs downwards. Okay, and so the final speed of the box, well, we can say the initial speed of the box equals 0 meters per second. The final speed we want to find out. Okay, so let's see if we can at first solve for the work done by the applied force. And real quick right here, I'm going to see if I can take this and move this. Oh, I'm trying to move some things around, but don't think I can. Nope. I was going to move these guys over a little bit, but that's all right. So we're going to solve for the work done by the applied force. So this is part A right there. Okay? So the work done by the applied force. Well, what is our definition of work? The definition of work is the force, the applied force, right, times the distance that it's moved through, and we have both of those, times the cosine of phi, which is the angle between them, right? The angle between them. Well, let's look at our applied force right here. That's upwards, directly upwards. And what's the direction of our distance or direction of motion? Well, that's upwards too, and they're basically, and they are in the same direction. So what's the angle between them? The angle between them is 0. And if you take the cosine of 0, what do you get? That becomes 1. The cosine of 0 is 1. So the fact that our applied force is exactly in the direction of motion, then we should be able to find the, then we should be able to know that the angle between them is 0. All right? All right. So from here we can pretty much ignore that cosine of 0 because it's 1. Well, let's find our work caused by the person applying the upward force. Well, what's our applied force? Our applied force is 52.7 newtons, right? 52.7 newtons divided by, or times what? What's our d? Our distance d is 1.60 meters. And I'm not sure if I'll have enough space to write that over to the right, so I'll write it below. And so the work done by the applied force upwards is 52.7 times 1.60. And I get a grand total of 84.3 joules. 84.3 joules. The work done by the applied force, that is applied and supplied by the person who's lifting it. Okay? Well, let's find the work done by gravity now. Okay? B, part B. I think we can fit this all in here. The work done by gravity. Well, that's the force of gravity. And what's the force of gravity? Well, that's the mass times the acceleration, right? That's the force of gravity. It creates that downward force that we call mg. mg times the distance that it's being moved through, and that's going to be d right there. But now this cosine of phi is going to be different, because previously our force was acting upwards and it was moving upwards, but now gravity is acting downwards and the object is moving upwards. So what is the angle between the direction of motion and the force that is applied by gravity? That green arc right there, that's 180 degrees, right? It's a 180 degree different direction that the two are pointing. And so we're going to have to account for that. The cosine, oops, I'm writing in green now. The cosine of 180, what do you get if you key in the cosine of 180? That's going to be -1, right? -1. So I put a slash through it, but it really doesn't cancel out. It just becomes -1. So our work done by gravity is going to be negative. And think about that for a second. It should make sense because you're moving upwards, but gravity is pulling down the whole time. And so gravity is fighting you as you lift up that box. And so gravity is doing negative work on that box. Well, let's key in our values and see what we get. M times G. Well, the mass is 4.10. And the G is, of course, 9.81 meters per second squared. And the distance is 1.60 meters times -1. What if we key all that together? I get a value of -64.4 joules. Gravity is fighting us the whole time, the work done by gravity. And so gravity is doing negative work on us as we lift the box up. And that should make sense because as you climb upwards, let's say you're climbing a ladder or you're climbing a mountain or as you're moving upwards, all right? You're displacing upwards, but gravity is fighting you the whole time. That's what makes climbing a mountain or a ladder somewhat difficult, right? Because gravity is doing negative work on you right there. Okay. Well, for this last segment, I am going to shrink this down a little bit because I need a little bit more space. Okay. Not that the last segment is hard, but it's going to be a little bit different, and we want to be able to find the final velocity right there. Well, so let's find the net work. Well, let me back up a little bit. We want to find the final velocity. Final velocity. What value have we just talked about recently that has velocity in it? Kinetic energy, right? Kinetic energy equals 1/2 mv squared. Well, we know the initial kinetic energy. The initial kinetic energy is 1/2 mv initial squared. And what's the initial velocity? Well, that's 0, right? So that's going to be 0. It should be at 0 right there. And so our final kinetic energy, K final, 1/2 mv final squared, that's what we want to find out. Well, actually, we want to be able to find out that final velocity right there, okay? So that's really what we're gunning for. Well, if you think back to just the previous slide, we came up with the work kinetic energy theorem. What the work kinetic energy theorem says is that the net work that is done equals the change in kinetic energy. That means the net work that is done on an object equals K final minus K. Not a very good minus sign, is it? Minus K initial. Okay. Well, first of all, that K initial is going to go away. It's going to become 0, right? But I was saying just a few minutes ago, and just a second ago, we need to find the net work that is done on this box right here. All right, well, what is the net work done? Well, the applied force applies 84.3 joules, right? Net work equals 84.3 joules, but the whole time gravity is fighting it, right? Gravity is applying negative 64.4 joules. So plus negative 64.4 joules of energy. That's going to be our negative work. And that's going to be equal to our kinetic energy final minus our kinetic energy initial right there. All right. What is our kinetic energy final? Well, it's 1/2 mv final squared. All right. What's our initial kinetic energy? Minus 1/2 mv initial squared. Oh, well, that's easy because our initial velocity in this case is 0, so that whole part just goes away. But we should be able to solve for the final velocity of our box right here because we know the mass of it and we know that the net work that is being done on that box. So let's see if we can solve for our final velocity right here. You know what? And I broke one of my own rules. I started plugging numbers in right here. Well, I should have put in, this is what I really should have written in. I should have written in the work done by the applied force minus the work done, or plus the work done by gravity, which of course is minus. I don't like plugging in numbers too soon, all right? But I did already right there. So what is our total net work that is being done right here? Well, we have 84.3 minus 64.4, and that's going to be our net work. But what we want to do before we do that is to solve for our final velocity, okay? So our final velocity, what we're going to do is we're going to take this 2 and multiply it up, right? So 2, it's 2 times work done by the applied force plus the work done by gravity. All right, so that 2 is going to get multiplied up, and our m is going to get divided down, right? So that's going to be put down here. And that's going to give us final velocity squared. Well, we don't want final velocity squared. We want just final velocity. So if we want just final velocity, we square root the whole thing, and that's going to give us our final velocity of the box. Well, let's go ahead and plug our values in right now and see if we can solve for the final velocity. So it's going to be 2 times. Here's now our 84.3 plus negative 64.4. That's our work done by gravity. All divided by the mass of the box, and that's 4.10 kilograms. And this is going to give us our final velocity of the box. And I get a value of 3.12 meters per second. That's how fast the box is moving after you moved it from this point to this point right there. Okay, so what we've used is the work kinetic energy theorem. We have equated work being done, net work being done. By the way, some is positive work, some is negative work, but the net work is the sum of all those works added up. So this came out to be 20-something, right? So the net work being done is a result of a change in kinetic energy, the final minus the initial. Well, the initial was nothing, and so knowing the work that was being done, we could figure out the final kinetic energy, being 1/2 mv squared, and solving for the v, we came up with 3.12 meters per second. So this is a good example of the work kinetic energy theorem. Net work is a change in kinetic energy. And this is going to be very, very handy in the upcoming types of problems. But I think this segment's been long enough, so thank you for following along. And if you have any questions, please make sure you see me, and I'll see you on the next one.